Translation from one subject to another. The procedure of the previous section essentially is one of the translations. We begin with a known trigonometrical fact that the sine rule is not inconsistent with the cosine formula. We translate into the language of the algebra. We translated into the language of the algebra and find that it must be possible to deduce one set of the equations from another. We have been led from the familiar at any rate to anyone who has done school trigonometry within the last 2 or 3 years, to an unfamiliar fact. Wow! Tell me, what is this? We have not merely gained a new result, we have made somewhat sharper our view of the old result, not inconsistent with, has been sharpened to, can be deduced from. Ha ha ha. Translation is a valuable exercise because before you can express a fact in the new languages, you must be clear what the fact is. Yes. At various places in this book, we shall try to state various things in such a way that they could be explained to an angel over the telephone. To explain geometry, for instance, without drawing any diagrams or invoking any physical ideas. Geometry, in fact, can be explained purely in terms of number. You may think this strange if you have been accustomed to think of the geometry as the study of the shape of the objects. But mathematics deal with the patterns. It is not concerned with the particular material in which the pattern is realized. Our ability to explain geometry to the angle means simply that we can, by means of numbers alone, exhibit the same patterns as those that occur in geometry. Wow! Like the wireless commentators, we could explain to the angle the progress of the football match. By giving the score and saying square 7. We could not, however, explain to do it what being kicked on the shin left like. As an example of the translation, I will try to translate into the algebra the fact that the cosine squared theta never exceeds 1. Yes, you're right. Again, as an example of the translation, I will try to translate into the algebra the fact that the cosine squared theta never exceeds 1. Please look at the diagram right now. To get away from the geometrical ideas, we will make use of the graph paper in figure 5. Let O be the origin, P the point AB, and large P the point, small AB, and large Q the point, small xy. This gives us a triangle, large OPQ, and anything there is a B said about this triangle cannot be said in the terms of the numbers small a, small b, small x, small y. Yes, that is to say, in terms of algebra, yes. It will be convenient to use small p for length of large OP, small q for the length large OQ, and r, small r, for the length large PQ. Of course, small PQR can be expressed in terms of the small ABXY by graphing the Pythagoras to the triangle large ONP, OSQ, and large PMQ. We have the very well-known result. Yes. Tell me. Small p squared equals small a squared plus small b squared. Small q squared equals small x squared plus y squared. Small r squared equals open parenthesis x minus y close parenthesis squared plus open parenthesis minus y open parenthesis y minus b close parenthesis squared. If the angle between large OP and OQ is called theta, we can find cosine theta from the formula 2 small pq cosine theta equal small p square plus small q square equal small r square. On substituting for small p squared, small q squared, and r squared from the three equations above, all the equation terms cancel out, and only 2ax plus 2by remains. Wow! So we'll have a small pq cosine theta equal small ax plus small by. Small p and q contain square roots if we express them in terms of the small abxy. However, as we want to express the fact that cosine squared theta never exceeds 1, we shall be squaring away. We thus find that open parentheses ax plus by close parentheses square cannot exceed small p squared q squared. That is, open parentheses ax plus by or close parentheses squared never exceeds open parentheses a squared plus b squared times open parentheses x squared plus y squared. Wow! Wow, yes, this is very basic. This is a purely algebraic result. We may express it by saying for the real numbers, open parentheses a squared plus b squared times open parentheses x squared plus y squared minus open parentheses ax plus by square close parentheses square is never negative. Is never negative. Ha ha ha. Why is it never negative? The above statement corresponds roughly to the trigonometrical statement that 1 minus cosine squared theta is never negative for real angle theta, but this expression is the same as sine squared theta. We are familiar with the fact that the square of the real numbers are never negative. Yes! We are thus led to expect that the algebraic expression above may very well be squared, and so it is. It is no great labor to multiply it out completely. Of the 7 terms so obtained, 4 cancels. Those remaining are equal to open parentheses bx minus ay close parentheses square. This can never be negative, and we have thus proved our algebraic result directly without any appeal to trigonometry. Our result may be written open parentheses a squared plus b squared times open parentheses x squared plus y squared minus open parentheses ax plus by close parentheses squared plus open parentheses bx minus ay close parentheses squared. Wow. This identity holds for all numbers a, d, x, y. In chapter 4, we shall return to this identity and see in what way it can be generalized. Wow, thank you very much.